On December 27, 2004, something happened in deep space that physically changed planet Earth. A star, 50,000 light-years away, cracked open. Not a supernova, not a collision, just a crack in its surface, lasting less than a fifth of a second. In that fraction of a second, it released more energy than our Sun has produced in the last 250,000 years. The blast traveled across half the Milky Way. By the time it reached us, it had faded to almost nothing. And it still compressed our planet's magnetic field. It still changed our upper atmosphere from night to day. Scientists watching their instruments thought their equipment had broken. It hadn't. That star was a magnetar. And it's just one stop on a tour of places in this universe so extreme, so far beyond the physics we experience every day, that the numbers will stop making sense. And that's the point. Because the universe isn't playing by our rules. Today, we're going to travel from the coldest place that has ever been measured, through the densest matter that can exist without collapsing into a black hole, all the way to a burning core 10 trillion degrees hot. A temperature so high it would vaporize the concept of temperature itself. Let's go. Before we get to the violence, we need to start somewhere quiet. Somewhere that shouldn't exist. 5,000 light-years from Earth, in the constellation Centaurus, there is a dying star. It's been shedding its outer layers for about 1,500 years, blowing gas outward at roughly 500,000 kilometers per hour. That's fast enough to circle the Earth 40 times in a single second. Here's the thing about gas expanding that quickly. It cools down. Fast. In fact, it has cooled down so dramatically that astronomers couldn't believe what they were measuring when they first studied it in 1995. The temperature inside this nebula, called the Boomerang Nebula, sits at -272 degrees Celsius. That's one single degree above absolute zero, the lowest temperature physically possible in the universe. For context, the deepest cold of outer space, the background glow left over from the Big Bang itself, sits at about -270 degrees Celsius. The Boomerang Nebula is colder than the background temperature of the entire universe. That's not a small thing. Every corner of space, every void between galaxies, every patch of nothing between stars, all of it is warmer than this nebula. It is, as far as we know, the only naturally occurring place in the observable universe that is colder than space itself. How does that happen? Think about what occurs when you spray an aerosol can. The gas inside expands rapidly as it leaves, and the can gets cold in your hand. The Boomerang Nebula is doing that same thing, but on a cosmic scale, and it has been doing it continuously for 15 centuries. The dying star at its center has been losing mass about 100 times faster than other similar stars in their final stages. All that material is being flung outward at incredible speed. And as it expands, it drops toward a temperature that nature almost never reaches. Scientists using the Atacama Large Millimeter Array in Chile confirmed the temperature a decade ago. The nebula isn't warming up yet. The cosmic refrigerator is still running. But here's something worth sitting with. We live in a universe where a single star, dying slowly over 1,000 years, has created the coldest place we have ever found. Not in a lab. Not in a particle accelerator. Out there, in open space, naturally. The universe is strange in the cold, but where it gets really strange is when things get heavy. Picture the Sun. A ball of gas 109 times wider than Earth, with enough mass that if you replaced our planet with a marble and the Sun with a basketball, that basketball's gravity would still hold the marble in orbit. Now collapse that entire basketball into something the size of a city. Not the gas, the mass, all of it, packed into a sphere about 20 kilometers across. That's a neutron star. When a massive star runs out of nuclear fuel, it can no longer support itself against its own gravity. The core collapses in under a second. The outer layers bounce off this newly compressed core and explode outward as a supernova, one of the most violent events in the cosmos. But the core remains, this impossibly dense remnant, and it becomes a neutron star. The density inside a neutron star is hard to put into human terms. 1 teaspoon of neutron star material would weigh roughly 10 million tons on Earth. Not because of some exotic property, because the matter is compressed so tightly that the electrons of every atom have been forced into the protons, turning almost everything into neutrons packed shoulder to shoulder, with nothing in between. A neutron star's surface gravity is about 200 billion times stronger than Earth's. If you fell toward one from a meter above the surface, you would hit it at approximately 2 million kilometers per hour. Neutron stars also spin fast. A newly formed neutron star can rotate hundreds of times per second. This isn't a quirk, it's conservation of angular momentum. The same reason a figure skater speeds up when they pull their arms in. The original star was enormous and rotating slowly. When its core collapsed to the size of a city, all that rotational energy went with it, and the spin became extreme. These spinning neutron stars emit beams of radiation from their magnetic poles, like a cosmic lighthouse. When those beams happen to sweep past Earth, we detect them as regular pulses, and we call them pulsars. For decades, astronomers assumed neutron stars were strange, but relatively uniform. They were wrong, because lurking within the population of neutron stars is a subclass so extreme that it makes ordinary neutron stars look tame. A subclass where the magnetic field doesn't just guide radiation, it reshapes the physics of everything around it. They're called magnetars, and one of them already changed Earth from 50,000 light-years away. A neutron star's magnetic field is already extraordinary, about 1 trillion times stronger than Earth's. That alone is a number that means nothing in everyday experience. A magnetar takes that and multiplies it by another 1,000. The most highly magnetized object ever measured by science is a magnetar called SGR 1806-20. Its magnetic field has been measured at over 1 quadrillion Gauss. Earth's magnetic field sits at less than 1 Gauss. The Sun's reaches about 5. This magnetar runs at 1 quadrillion. Astronomers Robert Duncan and Christopher Thompson first theorized these objects could exist in 1992. The idea was treated with some skepticism. By the late 1990s, observation had confirmed they were real, and then 2004 happened. On December 27th of that year, a crack formed in the solid crust of SGR 1806-20. When a magnetar's field becomes stressed beyond the breaking point, the crust can shift, releasing what's called a starquake, similar in concept to an earthquake, but driven entirely by magnetic stress rather than tectonic pressure. The energy released in that one event, in approximately 0.2 of a second, equaled what our Sun radiates over 250,000 years. The burst traveled across the galaxy at the speed of light. When it reached Earth, it was 50,000 light-years away and had been spreading through space the entire time. It still compressed our magnetic field. It still ionized our upper atmosphere, briefly mimicking the conditions of daytime at night for instruments measuring the ionosphere. If that magnetar had been 10 light-years away rather than 50,000, the resulting burst would have stripped our ozone layer and triggered a mass extinction event. The nearest known magnetar is about 9,000 light-years away in the constellation Carina. Scientists estimate that over 1 million magnetars may exist unseen in the dust lanes of the Milky Way, too faint or too quiet to detect. What makes magnetars so physically bizarre is not just the field strength, it's what that field does to matter. Atoms near a magnetar are stretched along field lines into long, thin cylinders, barely resembling normal atoms at all. The vacuum of space near a magnetar becomes polarized, meaning even empty space behaves differently in its presence. An astronaut approaching one would have the iron in their blood pulled toward the star before their body could register what was happening. At a few thousand kilometers away, the magnetar would remain just a dim point of light, but every credit card in their pocket would be instantly erased. A few hundred kilometers closer, and every atom in their body would be distorted beyond function. Distance is the only protection from a magnetar, and in this universe, the distances are generous. For now. But if magnetars represent the universe at its most magnetic, what does the universe look like at its most hot? For that, we need to leave the Milky Way entirely. 2.4 billion light-years from Earth, there is a point of light visible through backyard telescopes. It was catalogued decades ago as an unremarkable star. When astronomers studied its light closely, they realized it wasn't a star at all. It was 3C273, the first quasar ever discovered, and one of the most extreme sustained environments in the observable universe. A quasar is what happens when a supermassive black hole is actively consuming surrounding material. Gas and dust spiral inward in a disk, and as that material falls, it heats up through friction at an almost incomprehensible rate. The accretion disk around the central black hole begins to glow. Then it blazes. Then it outshines everything around it. 3C273 shines approximately 100 times brighter than all the stars in its host galaxy combined. You could detect it from almost anywhere in the visible universe. In 2016, an international team of astronomers measured the temperature of the plasma in 3C273's core using a combination of ground-based radio telescopes and the space-based radioastron satellite. The result was 10 trillion Kelvin, a measurement so high that it exceeded what the existing theoretical models said was possible. To compare, the surface of the Sun sits at about 5,500 degrees Celsius. The core of the Sun reaches about 15 million degrees. A neutron star's surface temperature is around 1,000,000 degrees. The plasma in the center of 3C273 measured 10 trillion. That's not a typo. As that plasma gets pulled in and heated, some of it gets channeled along the magnetic field lines of the black hole and fired back out as relativistic jets, beams of matter moving at close to the speed of light, shooting out for hundreds of thousands of light-years into surrounding space. These jets carry so much energy that they reshape the galaxies around them. Quasars are the most persistently luminous and hot objects in the universe. They can burn for millions of years. And they remind us that the universe produces extremes not just in brief flashes, but in structures that endure. But for a brief flash of pure energy, nothing in the known universe comes close to a gamma-ray burst. Scientists estimate that a gamma-ray burst releases, in roughly 10 seconds, 100 times more total energy than our Sun will produce across its entire 10 billion-year lifetime. In terms of raw luminosity at peak, they are 1,000,000 trillion times brighter than the Sun. They are, second only to the Big Bang itself, the most energetic events we know of. They form in at least two ways. When the most massive stars collapse and die, the core can form a black hole so suddenly that the resulting explosion punches jets of radiation through the star at close to light speed. These jets, when aimed toward Earth, appear as a brilliant gamma-ray flash that can outshine entire galaxies, visible from halfway across the observable universe. Short gamma-ray bursts, lasting under 2 seconds, are produced when neutron stars in binary systems spiral together and merge. In October 2022, a burst designated GRB 221009A was detected. Astronomers called it the Boat, the brightest of all time. It released so much energy that it saturated detectors across the world and in orbit simultaneously. Some instruments simply stopped working because they couldn't handle the incoming flux. It came from about 2 billion light-years away. We are lucky, again, that distance was involved. The universe began around 14 billion years ago. In that time, it produced a nebula that is colder than space itself. Stars so dense a teaspoon of their material would crush a building. Magnetic objects that reshape physics at a distance. Sustained fires 10 trillion degrees hot. And explosions so bright they blind the instruments of an entire planet from 2 billion light-years away. None of this required anything unusual. No rare exceptions. Just physics, applied at scales we have barely begun to measure. There are places in this universe that operate so far beyond ordinary experience that the numbers only gesture at the reality. And somewhere out there, in the parts of the sky we haven't studied yet, there are almost certainly environments that make everything on this list look quiet. If you want to know more about the objects that sit at the edge of what physics allows, the places where time and space themselves start to break down, Subscribe to our channel so you don't miss the next video.